I will record it. So the net ionic equation that we're going to look at here, we've got silver nitrate, we've got potassium chloride. Now, what you're going to be doing, there's 5 steps. All right, there are 5 steps that I want us to follow for balancing and then writing out a net ionic equation. First one is predict the products. Second one is determine the solubility of everything. That's using the chart to figure out how, whether everything's going to be aqueous or solid. Third step, you're going to write out the total ionic equation, and I'll explain what that is. Fourth step, you're going to cancel out spectator ions. I'll explain what those are. And then the fifth and final step will be to write the net ionic equation. That's actually the shortest and easiest step. And no, you are by no means going to be required to label the steps or anything like that. I'm just, I want you to have it written out so that you can, if you ever get lost, here's where you reference. So, okay, first step, predict the products. Now, this is a basic double displacement reaction. All right, you look at it. Remember that the like charges will switch places. So initially, we're just going to say, I like to do the positives first. It doesn't really make a difference. You can switch either one. So in this instance, let's switch silver and potassium. So, I'm just going to write this here for you. So please, when you do that, remember, you're trading the places. So you'll write K NO3 plus AgCl. Now, the first thing to remember is that when you write the ionic formulas, you must crisscross the charges. Don't forget to do that. You must make sure everything works out. So in this example, K is positive 1, NO3 is negative 1. You crisscross them. It's 1 to 1. Same thing for silver and chloride. Is everybody clear on that? How you're doing getting these formulas? Next, we might want to amend this, say predict and balance. So in this instance, everything's equal. It's all 1 to 1, so you're balanced already. There's a reason we're doing this one first. It's the easiest one I'm going to show you. So, all right, next step, solubility. So you get your chart. All right, you get your solubility chart, or you apply the solubility rules if you have those memorized, which none of you do in here. And you're going to just look and say, all right, what's soluble, what's not. So, silver nitrate. Remember, I already told you everything for nitrate, all right, or everything for nitrate is aqueous. You can't even see it.
I'm sorry.
Yeah.
What did we use? I thought we used KNO3. Which one did we use?
You have to find the solubility for all 4 of these things.
Oh.
You have to find the solubility for reactants and products, just so we're clear. So then you look up potassium chloride. That's one of the more soluble things around. I can tell you that already. Potassium nitrate. We already said all nitrates are soluble. Again, if you're not sure though, please just refer to your chart. All right? Do not hesitate to refer to your chart. Notice all the potassiums are soluble as well. Anyway, so okay. Oh, one other thing. I've actually noticed every year I say soluble a lot, and sometimes kids think that the S means soluble. What does the S mean, people?
Solid.
Solid. Okay, good. Yes.
Yeah, we know it's solid.
And then last but not least, you've got the silver, you've got chloride. So you've got silver and you've got chloride. That's a solid. Now, you're going to remember silver is usually solid.
Wait, what's chloride again?
ClO3. Now, you look at this, you do this. So we've now done number 1 and number 2. What I'm going to do is rewrite the equation down here simply because I need to be able to reference it below all this stuff. All right, so there's our equation. It's predicted, it's balanced, it's got the solubility done. All right, so step 3, we're going to write out our total ionic equation. Now, thankfully, this part this part doesn't require a lot of, like, it's pretty straightforward. All you need to do, you are going to separate everything that is aqueous. What do I mean by separate? I mean you're going to break it apart between the positive and negative ions and write it out in this really long total ionic equation. So, the way it'll work, AgNO3 is aqueous. So what you'll do, you'll write Ag. It's got a +1 charge. Its phase is aqueous.
So we just
Write a plus. You're just splitting them up where you have the where the ionic compound is. Nitrate. It's a -1. It's a polyatomic ion. Please don't forget about the polyatomic ions.
Polyatomic ions, when you move them across the equation, does the
They never separate. No.
yeah, you can't. So the little number on the side.
Yeah, that stays.
That stays.
Yeah, you got it. Good job. Now, yeah. So please remember when you do the polyatomic ions. When you do the polyatomic ions, you need to remember that they are not going to be separating ever. Like NO3 just stays NO3. Mirna, what?
Well, how do we?
Sure is right.
Yeah, that was.
How do I know the silver's aqueous? So this phase, this applies to both.
Alright.
So like this phase goes to both things, and if it's aqueous, that means that this splits up. All right. If it's a solid over here, which we'll get to, it does not split up then. So then we have to say it's aqueous again. Then you keep going. Yeah, it takes a lot of space. You do the same thing over here. All right, that's +1. Cl is -1. So you do that. Then on the other side, you've got your potassium. It's aqueous plus NO3.
Do we have to write the charge?
Yes. Then, lastly, you get to AgCl. It's a solid, so you don't separate AgCl.
So you can't write on charge.
Yeah, because it has no charge. It's not an ion. It's an ionic. It's staying in solution. It's a compound in solution. Like it's not breaking apart. It's not dissolving. So okay, you did all of this stuff. All right. So we did all this stuff. Now, the next step that we're going to do. All right, we are going to figure out our spectator ions. Now, I'm going to give you a very long description of what a spectator ion is when we're done with this problem. For right now, the really simple version is that you just want to cancel out everything that is the same on both sides of the arrow. So you can make a little note. It's just on both sides. Or if you could say, you know, present in reactants and products. And then you might want to make one other little note. They don't react at all. So, the arrow is our dividing line. All right, the arrow is what we sort of use to divide. So, let's look and see what we got that's exactly the same. Do we have silver on both sides exactly the same? No. It's silver is an ion here. It's in a compound here. You have nitrate, NO3. It's exactly the same on both sides. Cross it off. That's a spectator ion. Potassium, both sides. I should write a little 1 there. So both sides. Cancel that out.
So you just keep solids, basically?
So you keep the solid and you keep whatever reactants make up the solid, yes.
Alright.
Now, we've canceled out everything that's not reacting, and I'll explain what it means in a minute. So, final step, write out your net ionic equation. This part is the easiest part. All you do, copy down everything you didn't cross out. Ag +1, aqueous plus chlorine -1, aqueous, produces solid silver chloride.
So we actually have to write the charge.
Yeah, because when they're in solution, they are written as ions, and you must write that. It's just good practice to get into because you get more advanced. You're going to need to be writing it out anyway. But
So
solid, you don't take the AG and the CL apart?
No, so because the solid means like it's like if I threw that pen into a thing of water, it's going to stay a solid, right? Same concept with these chemicals; they don't break apart. So what I want to show you now is, to answer your question, like what's the point? Like why are we doing all the net ionic stuff? So let's imagine that we have our beaker of water. All right, so we got our little beaker. And remember how I said all of this is happening in solution?
Yes.
Answering your question, listen. Now, we are putting AgNO3 and KCl into our solution, all right? So we're going to put AgNO3 in here. And remember, we said that was aqueous, and KCl, we said that was aqueous. Now, here's what occurs. Okay, after a little while, they have now broken apart into Ag plus, NO3 negative, K plus, Cl negative. So, they're all floating around in here. Now, you do have to remember that there's not just one silver, one nitrate. There's, so many, it's almost, you can't even imagine how many there are floating around. So what occurs here is that now things start to move around. Like they all start kind of randomly moving in every little direction. There's a lot of them. So that means every once in a while they're going to bump into each other. All right, now we saw that the solid thing that forms in the end, all right, we saw that the solid thing that forms at the end of all this, so let's go down here now, was AgCl. That forms a solid. So that means that when the silver bumps into the chlorine, you get a solid forming. However, when silver bumps into nitrate again, we've already established that's aqueous. It doesn't happen. Nothing. It doesn't do anything. All right, we've established that when potassium bumps into chlorine, nothing will happen because it's aqueous. When nitrate and potassium bump into each other, okay, we established in our problem that that is also aqueous, so they don't do anything. So you just end up with these things sitting there, sort of all, aqueous, dissolved. They're not doing anything. These are what we call spectator ions. And yeah, you must know that. Like that's on your test.
Wait, which ones are the spectators? Oh, the aqueous ones?
So the spectator ions are the things that don't react at all. They simply dissolve and then they do nothing.
So it's the ones that turn aqueous?
Yeah, it's the ones that turn aqueous that don't then form a solid. Because notice, they're not in the precipitate, and this is what we're going to call the precipitate. So other key vocab word for this unit. Precipitate. All right? That is the solid that forms in a double displacement reaction.
So
I don't know why I capitalized R there. Apologies. Hang on. So again, spectator ions are the things that don't react throughout the entire process. Like there was K, there was NO3 at the beginning. At the end, there's still K, there's still NO3 at the end. They've done nothing. They haven't reacted. They're just sitting there. They don't even react. That's why they're not part of the net ionic concept. All right.
does this only happen in double displacement?
Yeah, right now, yes. That's all we care about. Yeah.
So spectator ions are the ones you cross out?
Yes, the spectator ions are the ones you cancel out. And I know there's actually a question on your test. It specifically asks you what are the spectator ions in a reaction as opposed to like what's the net ionic equation. So one of them wants you to actually cancel them out, and that's all it cares about. Just I don't usually tell you guys that, but whatever. What?
The silver can never touch the potassium ever.
Well, so when the silver runs into it, yes, they will collide. I mean, not frequently because they're both positive. They don't really attract, but nothing, just nothing. I mean, that's the point. They run into each other, but there's no bonding because they're both positive. There's no attraction, so nothing happens. Casabia, what'd you want? Didn't you have your hand up a minute ago? Oh, I was hopeful. Never mind. So, anyway, Any other questions on like this? Yes.
Could you have done all that just by looking at the formula?
Yes, I mean, with me now at this point, like I can look and say, okay, what's solid? If you know the solubility rules, it's pretty straightforward to do it. Like once you get really comfortable with it. But I don't know if I'd encourage you to do that just yet.
So
Unless you get it, it's fine.
you balance, then you just find what the solid is, and everything else is a spectator, right?
Yeah, reasonably. Yeah. Now, let's do one more that's a little bit harder. So now you look at the last example. Well, the second to last one we're gonna do, but the last really long one. Now in this case, I gave you the solubility of the first two. So remember with double displacement, remember your two positive things or your two negatives are going to trade. It doesn't matter. Make sure when you write these out that you write them out correctly again. So sodium goes with NO3, and sodium is +1, nitrate is -1. So when you crisscross those, it works out nicely. On the other side, you get magnesium with carbonate. Mg is +2, carbonate is -2. So again, they cancel out. Again, that's very nice. Now, are there any questions on that specific thing? Yes. Well, yeah, just one step at a time. So, question now. Where did the 2's go? Now, the whole idea here is that, remember, this 2 is written here because sodium is +1, carbonate is -2. So when you crisscross those, you end up with Na2CO3. Same thing over here. Magnesium is +2, nitrate's -1. So you crisscross, you get that. Now, obviously, remember, we don't carry subscripts over to the other side unless it's in a polyatomic ion. So what we must do here, we must balance the equation now. So now, the second part of this, you must balance it. So, you've established there's NO3 with a 2. There's Na with a 2. There's this formula right here where they're bonded together. Just put a 2 in front of it. Now, all of a sudden, you've got 2 NAs, 2 NAs, 2 nitrates, 2 nitrates. So now it's balanced. All right, that's where the 2's go. They remember, you don't write them as subscripts, you just write them as a coefficient in front. Like, please don't forget that. All right, so next, solubility. Now you look up the other 2. Now we've already established, if you remember, that sodium and nitrate, I mean, everything on our little chart, sodium soluble for, everything for nitrate is soluble, so I think that's definitely going to be aqueous. And then magnesium carbonate.
Wait, is the 2 actually there?
What?
For the sodium?
Yeah. So magnesium carbonate is solid.
Wait, why is it there?
This 2?
Yeah.
Because you needed to balance out the things on both sides. Like, if you don't have this 2 here, then you would have 1 sodium here, 2 sodiums there. It wouldn't make any sense. Remember, you got to observe the law of conservation. No. You're talking about this 3?
Yeah.
That 3 only applies to the O in nitrate. Nothing else. This is why you're paying attention for this example still.
Okay.
Now, anyway, so you look at this. So the next step, break it all up. Write out the total ionic equation now. So now you get this is the long step, and this is the step that you might want to try to skip. But if you skip this step, I worry that you might not get the spectator ions part right sometimes. So that's why we do this. So total ionic now. So Mg, it's going to get split up right here. So it's Mg +2 because that's a positive 2. That's its ionic charge. It's aqueous. Now, right here, notice we've got this subscript 2 for magnesium, or nitrate. Here's what you do. All right. The subscript will now go in front of the ion in solution.
Why?
Because you have to indicate somehow that you have 2 nitrates, but it doesn't apply to magnesium, so you'll just now move it to be a coefficient.
Why can't you just keep it like that one?
And just what you do. It's just how you notate it. So you're saying you have 2 NO3s. Each one's negative, each one's aqueous. So when we do this again, you might want to make a note that the subscripts become coefficients for their respective ions. So same deal. This 2 will go out in front. It'll only apply to sodium, but it will go out in front. So 2Na aqueous plus 1 plus now CO3. That's a -2 again. Draw your arrow. Make sure you separate this. Now, this 2, the coefficient here,
For both.
remember that applies to both of our formula. So 2Na, and that is why we change these to coefficients so they match up. So 2NO3s like that. Remember, the coefficient applies to both. That 2 applies to both things. And you'll notice we're starting to run out of room because, yeah, these things take forever. Don't break up the final thing, the solid.
Wait, why not?
You never
What?
realized-
Well, because by it being a solid, that means it doesn't dissolve. Like, that's the whole point. Since it's a solid, it doesn't break apart into its ionic form. It stays a solid in solution. And after we're done doing this, I'm going to show you what that means, because we're going to do several labs next try where you make some of these things, and you'll see it. But I'll show you a few videos right now of, like, you know, how they look. Because I know you're like, it's a solid in water. It's kind of like if you put, like, it's, you know how sand, when you put it in water, it just stays sand on the bottom there? Same deal, kind of. It's sort of. So anyway, now you cancel everything out. So, you know, now, you know, cancel spectator ions. So, what is the same on both sides of our arrow? We've got 2NO3s, 2NO3s, 2 sodiums, 2 sodiums. So, our spectator ions in this case were 2 sodiums that were aqueous. I'm just labeling them in case a question asks you to do that, which I know it does. And 2 sodiums.
Well, what does the question ask you to do?
If it says what were the spectator ions. So, just to be clear, in this problem,
So everything that is crossed out.
yeah, those are our spectator ions.
The quiz.
That's a really bad looking cue there for both of them. Anyway. So,
You don't put 4, you put 2.
I don't think at that point it's not a big deal. You just want to know what species were canceled out. So then the final step, write your net ionic. So you write Mg plus 2 aqueous, and this will be our net ionic, plus CO3 -2 aqueous. MgCO3 is a solid.
Wait, so what's the difference between that and the other one?
What do you mean?
There was no difference.
No difference between what and what?
The last one that we used.
Coefficients.
That's it.
Well, you had a question on it.
Yeah, I know, but that's
Exactly.
it.
All right. Any other questions? Like that's kind of it. Yeah.
For the total ionic part,
Shh.
you don't really need to know the plus and the minus.
No, it's not that essential. The reason I make you do this is because when you go into AP, then it does matter. So that's why it's just better if you're used to writing it out.
That's right. I still don't understand why you put a 2 in front of NA.
All right. I'll show you that. I'll show you that later.
No, I'm serious.
No, I'm serious. I'll show you later. So the last example, the easiest example is this. No, I'm actually surprised nobody's asked this yet. Basically, so let's take a look here. This is only gonna take about a minute because what you're gonna do, predict your stuff. So you're gonna switch the positives like we've done. So you're gonna end up with LiNO3 plus KCl. They're all 1-to-1, so that's nice. Everything works out. There's no need to balance. But I am actually kind of surprised nobody's asked about this yet. But if you look at the solubility, so potassium nitrate, we've established that all the potassiums, all the nitrates, soluble. All right, lithium chloride is also soluble. If you can just take my word for it, the other two are also soluble as well.
So what do you do with those?
So if everything is soluble, so what you would say if everything is soluble? So yeah, make a little note. If all are aqueous, then no reaction occurs. So that looks terrible. That R just, what is that?
What is it?
So if all of the reactants and products, so again, when we say all, we mean both reactants and products, both. All right, then no reaction occurs. What it means basically is that if you were to break this out, you don't need to write this part unless you really, really are like a perfectionist. But if you were to break this apart into everything, like all it means is that you're going to end up crossing out absolutely everything. Stop. So you cross everything out, nothing happens. It just means that basically you could mix two things together and that's it, nothing. So no reaction. Like you're going to see these. Like be aware, you will see these. Like you don't, like some people, they do all the work, they don't actually ever think about the fact that it's all aqueous, and then they look back at the end, they're like, oh, I wasted time. Don't be that person. Brooke, what?
Also, like when that happens, just leave it blank.
Yeah, like you would just say on the problem, you would just be like, oh, if they're all aqueous, you just stop and you write no reaction, you're done. It's nice.